All right, everyone. Welcome to ASRG, bringing you the latest in automotive research, innovation, and education. My name is John Heldreth. I am the founder of Automotive Security Research Group, coming to you from Stuttgart, Germany. First of all, let me quickly introduce myself. As I said, my name is John Heldreth. I founded Automotive Security Research Group in 2017. I have worked in the automotive industry for the last 15 years or so now and focus my time on product or vehicle related security. I'm originally from Detroit, Michigan in the US of A, but today I'm living in Germany and working at Porsche Engineering. Just quickly, I'd like to talk a little bit about Automotive Security Group. The Automotive Security Research Group is a nonprofit organization focusing on the advancement of the automotive security industry. This is a community to support the coming together of two areas of competencies: the IT security market and the automotive market. This is a community for you, for the automotive engineer, for the IT security specialist, the beginner, the experts, the hobbyists, even for those people that might be in the wrong YouTube channel. This is a community of volunteers as well. Our entire organization is built on the volunteer efforts of the administrative staff and, of course, people like yourself. We are trying to remove the boundaries that can occur in the automotive security industry. This could be communication, borders, finding different ways to learn, new solutions, making good decisions, because at the end of the day, we all have the same goals: to keep our customers, our families, our friends, data safe and secure, which can only be achieved together. If you want to get more involved, make an impact on the industry, start your own ASRG location, participate in a technical committee, or be a part of a project, reach out to us. You can find out more information at www.asrg.io or send us an email at hello@asrg.io. Today, ASRG is more than 5,700 members. We're 38 locations worldwide in 19 different countries. This is pretty amazing. Since we started the year, I think it was 9 locations, and we had around 1,000 members. And going from 1,000 members to 5,700 members, it's really amazing for me. And I want to thank the community quickly, because this is a community for the members. This is for you to learn, to network, to get involved, be a part of something that maybe you can't be within your job. And so, while numbers don't really matter that much, the point here is that as long as the numbers keep increasing, we see that there's value being brought into the industry, to the academia, to the other communities which are also trying to accomplish goals just like ASRG. So I'm very happy have what has happened here in 2020. This being our last webinar and everything, I just wanted to say thank you, first of all, to all the members. Okay. This really can't be done without you guys, and we hope that all of this makes sense for you, that it brings you value. So reach out to us. We really want everyone to get involved. This is a community for you. And so please just send us an email, get involved somehow. Take advantage of this opportunity. I also need to thank the administrative staff. The administrative staff is working for free. These guys are people in all of the different countries that you see here on the map, and they put in their own time to make ASRG what it is today. So I really appreciate that. These are the people behind the scenes making everything work. So thank you to the administrative staff for all your support in 2020. I'm looking forward to what we have going on in 2021 as well. So check back with ASRG. We have some really cool stuff coming next year. I don't want to say too much because there's a lot of things involved, but we have many different projects. We're working on a podcast. We're working on a newsletter and getting some marketing companies involved. So we have all of this exciting stuff going on. We need your support to make this thing huge. So get involved, be a part of ASRG in 2021. And since this is our last webinar for this year, I wanted to just say enjoy some vacation time. If you do have vacation, try to turn yourself off a little bit and relax, because it's very important to be able to be relaxed a little bit at some point. So I wanted to mention also here that we do have some new things going on in these different locations. San Francisco and Los Angeles have a new leadership team there. Really great, really excited about that. We also have a new location in Waterford, Ireland. So check it out. We have a new location in San Sebastian in Spain. We also have a new location in Germany, and this is Braunschweig or Wolfsburg, the headquarters of VW and surrounding areas. So, and there's one last one, Colombo. We have a new location, Automotive Security Research Group in Colombo, Sri Lanka. Really interesting stuff going on. So check it out, get involved, be a part of the movement, okay? So as I said, this is the last webinar of this year. 2021 is going to bring some new stuff, including new webinars. We have webinars booked until August next year, 2021. So first of all, if you'd like to give a webinar, if you'd like to present something, do some research, reverse engineering, reverse engineer a vulnerability or something like this, let us know. Get in touch with us. You can contact us at cfp@asrg.io, and we'll set you up in the schedule, discuss how things work, and then you can have your own ASRG webinar. But we have some really cool webinars coming up. January 7th, we have the 12 myths of automotive cybersecurity with Russ Belaski from GuardKnox. Going to be a really interesting talk here. GuardKnox security leader. January 12th, 2021, we have Cybellum. Cybellum is going to come and talk to us a little bit about the cybersecurity. I can't say exactly what it is quite yet. We haven't fixed the title, but as always from Cybellum, we're going to get something really cool. January 14th, Marco Donadio from GMV. He's actually the lead for Barcelona, Spain, ASRG. He's going to bring a very interesting topic as well. January 21st, harmonizing cybersecurity across the automotive ecosystem. Sounds really interesting from Nathaniel Maron, C2A. So guys, we have so many more coming up. Check the website. The new website has all the events on it. I have to also admit the new website is not quite 100%. So help us out. Let us know what's going on there, what issues we have, so we can also fix those. All right, so that's enough for me tonight. If you have any questions during the presentation, please add them in the chat window, and we will ask Gilad at the end. So it's my distinct pleasure to introduce to you Gilad Bandel from Arilou Security, and he's going to be talking today a little bit about Telematics Control Unit cybersecurity. The title is Telematics Control Unit Cybersecurity, a Battle on Two Fronts. So, Mr. Bandel.
Thank you, John. Good evening, everyone. Thank you for joining me. My name is Gilad Bandel. I'm serving as VP Product and Marketing for Arilou Automotive Cybersecurity. And this evening, we will discuss the specifics of the TCU cybersecurity. And we will see why the name battling on two fronts is very, very relevant. So, a bit of history. Going back to 1801, on March 21st, the 28th, which is the North Gloucester Regiment of the British Army, fought a fierce battle outside of Alexandria, Egypt. Now, during this battle, the enemy cavalry break through the lines and formed a two-sided battle. So those guys from the 28th were encircled and had to fight while they were fighting back to back. At some point, a order came, rear rank 28th, right face about, and the rear rank turned back, the front line fought forward, and after a fierce fight, they were able to win this battle. So this is to teach us that even in the most severe conditions, if you do things right, you can win and you can emerge victorious of fights which look lost. This is exactly the situation in which the TCU is. So the TCU, the Telematics Control Unit, is a device which is connected to two networks. From one side, it is remotely attackable via the cellular network. From the other side, it is with very intimate integration with the in-vehicle network. So it can be both attacked from the in-vehicle network. It can be used as a vehicle of attacking the in-vehicle network. It can be used in a method of using the cellular network to gain access through this device to the vehicle, and so on. We will discuss those things during the presentation. A few things to notice. We are moving from CAN bus to Ethernet. That means that there is an end-to-end IP network from the hacker's laptop somewhere around the globe to the last ECU. This is enabling and facilitating in many fashions the ability of any hacker to attack a vehicle. So speaking about the whole Ethernet, automotive Ethernet cybersecurity, we'll do it in a separate session, not today, but this is something which worth noticing. TCUs are in some cases an aftermarket device. That means a device which is not under the control of the OEM. It is just attached to the vehicle network. And we don't know exactly who wrote the software there and what means of security are available there. So this is another attack vector that can be used. It's a surface through which attackers can gain access to the vehicle. Now, they say that in presentation, you should come with numbers, and if you show a number, this becomes very, very reliable. So in this spirit, there is quite a few researches on this area. And if I take the average from a few researchers, 40% of the vulnerabilities in the in-vehicle network are in the TCU, and it is only second to the IVI. That doesn't mean that the IVI is more dangerous to the vehicle. Actually, the TCU is more dangerous to the vehicle because the IVI, even though it's more prone to be attacked and has more vulnerabilities, and it is connected in many cases to the public internet, it should not have clear access to the in-vehicle network. As of the TCU, the opposite is correct. The TCU has full access, very deep access, very intimate access to the vehicle network. So even though only 40% of the vulnerabilities are found there, the risk factor, and we'll speak in another session about TARA and how you run TARA and how you do vulnerability assessment, and how you measure the risk and how do you mitigate the risk and do risk minimization. But given so many vulnerabilities from one side and the damage that can be caused by a TCU, we end up understanding that the TCU is a very, very dangerous device. Now, we need to keep in mind that security is about enabling. It's not about disabling. So we could say take the TCU out, but no, that's not the case. The case should be that we should find ways in which we use the TCU to its maximum capabilities while doing this in a secure fashion. So we're going to speak today of how the TCU works, what are the attack vectors, and what should we do to protect the TCU so we have a working vehicle which works with excellent telematics in it. So let's look a bit at how the network looks like. We come from the internet. The internet can be something in a cloud or a laptop, a mobile phone, whatever. It goes through the internet. It can be public internet or it can be a private access point in the cellular network. Go through the, in this case, is the fourth generation LTE, but it can be other cellular networks as well, into the TCU. The TCU is connected, in this case, to the CAN bus. We will discuss other cases as well in which it's not CAN bus and there is a different topology. So in this case, the TCU has its own cellular communication and goes into the bus. So the incoming traffic from the cellular goes through the TCU into the vehicle. There is a theoretical case in which the CAN traffic can be used to attack the TCU and from there into the cloud, but that's a less appealing attack vector. I would not count this as my major concern, my major threat. If we look into the vehicle and how the net topology looks like, there are a few cases. A few cases of targets and a few cases of topologies. So one case is that the TCU is the target of the attack itself. And we want to manipulate and we want to take over the TCU itself. And this can cause damage which is more or less local. The most interesting case in which the TCU is a member in the kill chain. So it's a component in the kill chain. We go from the cellular network, we skip into the in-vehicle network, in this case, a CAN bus. And from there, we gain access to the ECU. So the TCU is compromised with the target of gaining access to internal in-vehicle network ECUs. It can be used as a relay. It can be used as a channel. It can be used in several fashions. Out of the ECU, out of the TCU, it can go through another ECU directly, or it can go through to the central gateway, and from there on, it can go to other CAN buses. And this creates a domino effect, an amplification attack in which we go from network to network, and we can reach other networks as well. One thing to mention is that when we speak about CAN bus, actually we should also mention other protocols which are used in CAN bus, such as the SAE J1939. So attacking a heavy-duty vehicle through the TCU and then using the J1939 is a viable scenario. So this should be regarded as well as a case that should be addressed when protecting the vehicle. Looking into a few more topologies. So on the left-hand side, we have a case in which the TCU is connected to a gateway. In this case, it can be an Ethernet gateway. And through the gateway, it reaches the ECU. So here we can think about protection later in two layers, one of them in the TCU itself, and the second layer would be in the gateway. We can offload the inspection that needs to be done by the gateway into the TCU, given that there are resources to do so, and therefore we can allow the gateway to protect more traffic if the traffic from the TCU is already inspected and cleared for traveling inside the vehicle. Another case is a connected gateway. A connected gateway is a gateway that has the cellular connectivity, while the TCU does not have any cellular connectivity. We see those topologies more and more frequent. So in this case, the attacker would go from the cellular network through the central gateway into the TCU, compromising the TCU, and from then on, reaching another ECU. In this case, it would be a bit harder to achieve this kind of attack, given that hopefully the gateway is doing its job and is protecting the traffic. But still, this is a viable attack scenario. And in this case, again, we can share the load between the gateway and the TCU in inspection, but obviously the gateway here is the first to encounter the traffic, and more of the load will be on the gateway. A third case is something that we call the TGU, Telematics Gateway Unit, which is a combined device which performs both the gateway function and the TCU function. So it's not just a TCU with a connectivity to the CAN bus, it performs the full gateway function. In this case, we would need a very strong CPU here to inspect the full traffic. It's the easiest case because there is one central place in which everything goes through. So in terms of cybersecurity architecture, it's the optimal case. However, you need a very strong CPU here. So whenever you design a new TGU, keep in mind that security requires lots of resources, and you need to plan a very good microcontroller with lots of power, or select a split configuration in which the gateway function and the security functions are performed in separate CPUs. Looking into the history, there were cases worth mentioning a few, but you can search yourself the others. There were most of them were published. It starts from just causing damage by bombing cars. It happened in the US, and it's 10 years old. We are a cybersecurity research team headed by our CTO. was able to gain access to a major OEM vehicle network using the TCU, and we were able to gain control over hundreds of thousands of vehicles. This was done by finding a set of vulnerabilities which were turned into exposures and generating attack vectors and kill chains. Pure communication needs through the through SMS. So we found a buffer overflow that could be used by SMS, and this way compromise a TCU, and we were able to take over the TCU and start a chain of actions using plain SMSs. Those of you who are familiar with modem commands, they are called AT commands. So we're able to access an AT command interface and more. So this was one of the Arilou achievements, and many people did not sleep for many nights once we presented those things. Part of them were achieved through vulnerability assessment, some of them by other means. And there were other cases like finding hard-coded credentials, exposing thousands of cars, retrieving information, retrieving location. There was a GPS case in which we could retrieve information about the location of the vehicle and remotely shutting down engines. So the TCU is the means through which those things were achieved. So let's look at the communication protocol. Let's drill down a bit into what happens there. On the cellular side, we have a cellular network, third generation, fourth generation, fifth generation. There are even lower protocols, as I mentioned, such as SMS, which can be used for those things. There are other cellular low-level protocols which cellular experts are accustomed, like SS structured service, USSD unstructured service, that might be used for generating attacks. Those are things that people are not using day by day if you are not in the cellular business. As I mentioned before, the IP is now standard IP when going to automotive Ethernet. For sure, the whole layer from the cloud to the TCU is IP, and it's going to be IP all the way to the last ECU. There are higher layer protocols. I want to relate 1 second to IPsec or TLS, if we're speaking about fourth layer. Those provide authentication, encryption, anti-tampering, and so on. But this is just protecting the channel. That means that if the end device, something in the cloud, was compromised, you have now a very, very secure channel on through which you can pass the malware into the vehicle. So saying that I have authentication and I have integrity and I prevent replay attacks and the information is encryption, it's nice, but that's all. It's better than nothing, but definitely it does not provide any protection against tampering with the internal information if the two end devices are compromised. We use other protocols on the way, such as telemetry for diagnostics, for FOTA. So there are many protocols here, especially when we move to automotive Ethernet. New software, new bugs, new vulnerabilities, new exposures, new risks. But the same holds for CAN bus as well when we speak of the in-vehicle network. When we look at the in-vehicle network, we mentioned CAN bus and the various flavors. We don't care which flavor it is, it's more or less the same. The same thing about security. SecOC, it's good, it's nice to have, but that's all. It does not provide any protection against the content of a compromised device. Heavy-duty vehicles use the SAJ 1939 and automotive Ethernet, as mentioned before. We recognize that in the vehicle there are other protocols such as LIN, FlexRay. Most, in our view, they are not relevant, and they are not going to be used as the tool to attack. So we should focus ourselves on the CAN bus and the automotive Ethernet. Moving on to the embedded positions. There are many things that can happen. It's not only through the network, and we should appreciate those cases as well. We can have a compromised boot sequence. If, for example, no secure boot on the way, and secure boot is a different subject, very, very interesting subject that we can discuss in a different occasion. Tampering with the storage, firmware updates, which are done either through the OTA or remotely or any other mean, can infiltrate and inject malware, and that malware might allow remote access. All kinds of vulnerabilities such as buffer overflow, open port, or other vulnerabilities. So the TCU can be compromised in many fashions. Some of them are similar to other ways to compromise ECUs, but the effect that we have when we compromise the TCU is much more severe. What can we do to defend? There is no one silver bullet. There is no one way in which we can provide 100% security, and there is no 100% security. But we can do quite a lot. And the fact that, and I promise not to say one word about the UNECWP 29. There were an infinite number of lectures and sessions on these subjects, and we're not going to spend time on it, except for saying that this is a pressure in the industry, and it's motivating the industry to take action. So there are many things that we can do, starting with secure by design, and developing process and hardening of the software and the hardware. There are many ways to do it. Protecting the links, preventing peer-to-peer. I'll give you an example of how peer-to-peer works, and why this thing should be prevented. The way that the cellular networks work in the TCU is that you have a private APN, access point name, that should be, in theory, a separate non-internet network. So if you have a fleet and you're a fleet owner, you can buy from the cellular provider, cellular service provider, a private APN. And then the communication is not on the public internet, not to the public internet, but on your private network. Now, that means that anyone can communicate with the security information and event management system at the SOC, the Security Operations Center. In theory, the communication should be with a tree topology. That means that any vehicle can communicate with the center, anyone from the center can communicate with any vehicle, but, and this is the but, the topology should be as such that no vehicle can communicate with another vehicle. So there will not be a we call it user-to-user communication. From our experience, it doesn't happen. So all you need to do to attack another vehicle is to buy a similar vehicle, take out the SIM, plug it into your attack device, and now you have access to all the vehicles that are connected to that APN. Again, this is something that seems simple, and it's clear to people that should be aware of those things, but from our experience, we find that many do not follow this advice. Secure boot is a must. And secure boot, again, we can speak about it in a separate occasion. It's a long discussion, very interesting, how to do it, how to optimize it. Host intrusion detection system to make sure that the device itself performs as expected. In addition, and in my view, this is the most important thing, you need an objective, dedicated, independent piece of software that would look at the traffic and detect attack scenarios, detect attack attempts. And this is the network intrusion detection system or intrusion prevention system. Can look at message formats, we can look at field ranges, change rates, can look at periodic message, if they appear on time, if they do not appear. We can do correlation between signals. We can find misbehaviors. We can make sure the messages are plausible. Those things obviously need to be aware of the vehicle context. So a vehicle which is in accessories will not behave the same as a vehicle in parking and will not behave as a vehicle while driving. And there are more things like cryptographic means and so on. So we're going to speak about them a bit later. How we do those things. The first question that we need to ask, and this is a policy of the OEM, do we do IDS or IPS? And this is a big controversy in the industry, because from one perspective, the OEM look at protecting the fleet. And the claim is that a driver has nothing to do and cannot do anything if there is an attack, a cyber attack detected, and they're also afraid of false positives. So the idea of the OEMs would be mainly a detect and respond. That means once something is detected, send this event to the SIM. We do their forensics, we do the analytics, find the solution, and send an updated version of software at a later time. From the other side, there are people both in the OEMs, mainly in the cybersecurity team, and regulation, which is looking at the individual vehicle. That means that we need to prevent attacks. We need to prevent it in real time. We cannot do it at a later time. This brings us to an IPS, intrusion prevention system. So we need to detect and prevent. This has the benefit that it can prevent damage. But from the other side, there is the fear that due to a software bug, there will be some dropped frames that should be passing. And therefore, the IPS itself can be by mistake causing an accident. So those are the considerations, those are the major fears that you might have. By the way, the IPS can take some other actions, not necessarily preventing the traffic from going. We can, for example, disable functions. For example, we can disconnect the vehicle from the network and take the vehicle to a garage. Disable any functions that have to do with communication, such as the IVI, the TPMS, the Wi-Fi, the Bluetooth in the vehicle, and this way creating some defense in the vehicle, even taking off any non-essential component in the vehicle, such as the windows, the air conditioning. I'm not sure that air conditioning is not a critical component in a vehicle, but this is the idea, like pressing a green button that says, now we do only the things that need to be done for the vehicle to reach at the highest safety level, the service center. So the question between IDS, IPS is a theological question in many respects. Depending who you're asking, you'll get a different answer. My approach to this is that the vehicle should have an IDS, IPS, and it should be approached with caution. That means it should be deployed as an IDS, taking the risk that things might happen. Roll it for a period of time, making sure that there are no false positives, and then gradually and remotely activating the prevention after we are sure that enough time passed and we got enough experience, ensuring that we do not cause damage to the vehicle or to the passengers or to the other road users. Let's look at the inspection that we can do. One inspection is on the cellular traffic. The cellular traffic comes in different protocols, and we need to monitor the incoming traffic into the vehicle. This is the most important thing that needs to be to be inspected. That means that we need to understand the protocols, we need to pass those protocols, and we need to look for anomalies or for behaviors or for signatures that look suspicious. The outgoing traffic from the vehicle, this is a possible attack scenario in which vehicles would attack the cloud. From my perspective, it's less interesting, and I would approach this only after the other components are protected, and leave this as the last item in the priorities. In security, we cannot do everything. We need to have the maximum protection with the minimum budget and within the constraints of the CPU and form factor and schedule and so on. So it doesn't need to be perfect. It needs to be good enough. If we look at the incoming traffic, then we can inspect the traffic that goes out of the TCU, and on the way inspect the traffic which goes into the TCU as well. So if for the cellular interface we have a Sentinel Cell, which is the Arilou product for protecting cellular interfaces, Sentinel CAN and Sentinel TRK for J1939 are the products which provide cybersecurity protection on the CAN bus, either for pure CAN bus or for J1939. And here inspection means inspecting the formality of the traffic, the signals, the values of the signals, ranges of the signals, how those signals behave with relation to the vehicle. If you get, for example, 1,000 kilometers per hour in a signal just because it's 16-bit, doesn't mean that this is physically possible. So someone probably did something very bad with your ECUs, and they are emitting information which does not make sense. If we're looking at the Ethernet, then on the cellular side will remain as before, but on the Ethernet side, we use Sentinel ETH, which is protecting the Ethernet. In this case, we see a TGU that has multiple functions. And in this case, we can get in one device protection both for the cellular and for the whole Ethernet ports connected to this device. So it's not only for the TGU, it would protect the whole CAN bus, the whole Ethernet network on the way. Inspecting the traffic which goes to the network. In this case, it can be CAN bus or J1939. As I said, we can do detection only. We can think about prevention. And there are other things to do which are not related directly to the inspection. For example, designing a network which has segregation, and the connected network is separated from the safety-related devices. So there are so many things that can be done and are easy to be done in some cases to reach our goal of security. This is another case. In this case, we have the TCU connected to a gateway. This solution, we can place the Ethernet security both in the TCU and in the gateway. In case this thing works and the gateway relies on the TCU, we can offload the inspection of the Ethernet traffic to the TCU. This way, we can free the automotive Ethernet gateway handling all the in-vehicle network traffic, which is, as it is, going to be more and more intense. And this way, the TCU can perform the specific functions. We need to keep in mind that there is no generic IDS. Each IDS needs to be tailored to its specific task, and the Ethernet protection inside the TCU will need to use different rules, custom rules, which are tailored for the TCU case, as opposed to the other rules which are in the Ethernet gateway. By the way, this holds also for the DOIP interface for the diagnostics. The rules that apply to the external diagnostic port are different than the rules that apply to the in-vehicle Ethernet. Just to give one example, the IP addresses in a vehicle are static, so it's all deterministic and predictive, while on the diagnostic port, the IP address is dynamic, and the MAC address of the external device is dynamic. So you cannot set strict, static, predefined rules on the IP address and MAC address of the testing equipment that is connected to the gateway. And the same as those rules are different, the in-vehicle rules are different, and the TCU rules are different, and each of those instances need to have its own set of tailor-made and customized and adapted rules. This is another case. In this case, this is a connected gateway. A connected gateway needs to protect the traffic on the cellular side and on the in-vehicle network going to the TCU. In this case, we really need a good gateway because it stays in the front. And this is the gateway that needs to protect everything. And we need to apply here both the cellular rules and the TCU rules and the other rules in the vehicle. The fact that the TCU is inside the vehicle means that it is already after the first layer of protection. We can do some additional protection there, but it's less important because the first line of defense is with the connected gateway. So if we summarize, we have two types of interfaces, the cellular interface and the in-vehicle network. The cellular interface is IP over cellular in all cases. And there are two directions, the incoming and outgoing. In the in-vehicle, we have two major protocols, the CAN bus and the Ethernet. And again, we have two cases of incoming and outgoing. In some cases, the TCU has a cellular modem. In some cases, it does not have because it is relying on the central gateway, connected gateway for the cellular interface. We need to decide where we do the implementation. We can do it in the TCU or in the TCU and the gateway. We can decide whether we do prevention or detection. In some cases, we can do only detection or only prevention. And there are, as we spoke during the presentation, in some cases, if we have a first line of defense, which is the central gateway, then the TCU is behind the central gateway, needs less protection on itself because it relies on the gateway. In any case, the system needs to be protected. And the architecture needs to be as such that it takes into account the fact that there are attacks that can originate from the cellular network, and those attacks can reach the vehicle. And the easiest way to reach the vehicle is through the TCU. If we summarize this thing, then it's obvious that both tier ones and OEMs need to implement the proper security in all the telematics related domain. It can be done in the TCU, it can be done in the gateway, it can be done in both, depending on the topology. What I think that should be done is that security should be in mind day zero, and the architecture and the network topology and the component selected for this TCU and for the gateway, and the roles that each one of them is supposed to take in the cybersecurity protection should be from conception, from day zero. You cannot have a topology and an architecture and then one day wake up and ask yourself, where do I fit here the cybersecurity? It does not work this way. It needs to be done from day zero. So both the tier one and the OEM needs to select the tools and the architecture to make this work. It can be a good idea for an OEM to select the product that performs the IDS IPS function ahead of time and implement it with the tier ones in the various devices. So this way there is one source, one methodology which is coherent throughout the vehicle and is in charge of the intrusion detection and intrusion prevention. The other alternative that you have a few devices, the gateway, the TCU, the IVI, and each one of them come with their own cybersecurity, and you can hope that they work together and provide a good security, even though they are not correlated. We at Arilou provide several solutions for this area, including the Sentinel CAN, which is protecting the CAN bus, Sentinel TRK for the heavy-duty vehicles employing SAJ 1939. For the Ethernet, the Sentinel ETH, and for the cellular, the Sentinel Cell. We have other products as well. We'll not discuss them today, but compression, CAN-bus compression is a very interesting thing, and we can as well have a session about this thing as well. So thank you very much, everyone. We're now open for questions. So John, if there are any questions, I'll be more than happy to answer them.
All right, Gilad, thank you so much for the really interesting presentation. And kind of this is something where you don't need to have physical access to the vehicle, right? So
not at all, not at all. All the attacks that we carry out through the cellular network. We assume that let me take one step ahead. There is the issue of hardware protection and hardware tampering and anti-tampering and having those RFIs and RFPs, which require a lot of hardware hardening. And my question is the following: if I want to harm someone, what's easier? To come with all the electronics and wisdom and tamper some hardware, or plant a bomb under the seat of the driver? So the physical attack on a vehicle through hardware seems to me less relevant, because the other alternative is physically to plant a bomb on the car, and it's so much. We're not going to discuss. There won't be a lecture how to prepare a bomb at home. But if someone really wants to do some damage, it would be remotely. It would be using some form of RF, and the first choice would be cellular, because it can be done from anywhere. If we speak about TPMS or Bluetooth or Wi-Fi, you need to be really, really close to the vehicle, and you can attack one single vehicle. If you do it from the cellular, you can attack the whole fleet.
Yeah.
So yeah,
definitely, this is exactly the problem with when you do risk assessments and stuff like that, and then you look, okay, what kind of damage can be done? Okay, do I need physical or remote access? Well, okay, remote. And then the second thing you look at, or is it a single vehicle or does it scale? So in this case, with attacks over or through the cellular networks, this is really something that we need to pay attention to. Just like you said in your presentation, this needs to be taken care of. So actually, we do have one question from the audience. I'm not sure if you'll be able to answer it, but how many TCUs are currently deployed globally? I think he's kind of looking for an idea of what type of attack vector we're looking at here.
Okay, so I don't have an answer to this question. In general, I can say that as far as I know, all the heavy-duty vehicles have TCUs. In some countries, it's already compulsory to have, even in passenger vehicle TCUs. I'm looking at the future market. So let's separate the question into two. What is the total number of TCUs and what is the total addressable market? So the total number of TCUs is a bit less relevant from our perspective, not because they cannot be used as a tool to attack, but because the chances that anyone can influence and change the software of a TCU, which is already in a vehicle on the road, I'm not saying that it's impossible, but it's not very likely, to say the least.
Mm-hmm.
So we should look at the question. Now I'm acting as a politician, and I'm saying the question should be, this is not the question, the question should be, how many new TCUs are rolling on new vehicles? and the number should be, in my view, around at least 40 to 50% of the new vehicles will have TCUs. And this is the thing that we need to focus ourselves where we can make a difference and where we can influence the result. And there is no practical way in which I can start working on old TCUs. Those guys should hope that nobody's going to attack them. And for new people, they should have the trust in their OEMs that those OEMs included sufficient cybersecurity protection of the vehicle and especially on the TCU.
Okay. Yeah, definitely. There's one more question, or maybe two more here. Scott is asking, is there any utility in having potentially two TCUs in an architecture? Maybe one just for vehicle updates that limits connections to trusted OEM backend servers with certificate pinning and stuff like this, and maybe another for user data. Any comments on potentially segmenting the communication channels here?
So when you add a second TCU, you double the risk. So I'm not sure that you would gain more security by adding one more channel, access channel into the vehicle. So I understand the reasoning that you might say each TCU would have a different role. And this way you can minimize the collateral damage that one TCU can create. But in my view, first of all, OEMs are very, very sensitive to pricing. So adding another cent to the BOM needs the approval of the CEO. So adding another TCU, for sure not for passenger cars, maybe for the heavy duty vehicles, which are more expensive, and adding a few more cents would not make a huge difference. But in my view, I would try to provide good protection to one TCU, then medium rate protection to two TCUs. You won't gain more value by having two TCUs in a vehicle.
Okay.
But thank you for the idea.
Yeah,
I appreciate it.
Actually, I think it's an interesting question here. I mean, adding complexity to a system doesn't necessarily solve the problem of security, but excuse me, having a second channel here where might be an interesting solution to some of the security issues that we have.
I'm a big fan of the KISS concept. KISS standing for keep it simple, stupid. So if it's not going to be simple, it's simply not going to be.
Yep. And I think, Scott, basically every OEM just kind of cried a little bit because the idea of adding another TCU to the car, just because of cost. But really nice question. Thanks, Scott. Good, Gilad. Then I have a few questions myself for you, if you have some more time.
Please do.
So, first of all, how do you see the relationship between V2X and IVI protection and TCU protection? I mean, is this kind of the same thing, or is there differences between these things?
Very different and very similar. All those devices are connected devices. So the basic concept that should be applied is the same, that each and every one should be protected, both on the in-vehicle side and on the cellular side. And not necessarily cellular, but because V2X is has also the SRC, which is not cellular, but on the outside of the vehicle. Each and one of them have different attack scenarios, different behaviors, different professional things that need to be addressed. Those are different protocols. With a V2X, it's not even IP. So yes, you could use the same concepts and the same ideas, but definitely it's a different ball game. For example, the V2X, we're speaking about plausibility and misbehavior, and we should regard the V2X mainly as another sensor, which is external to the vehicle. And we need to make sure that those the information which we receive from the V2X is in line with the experience of the vehicle. So we should do some sensor fusion between the external sensor and the in-vehicle sensor. So the whole V2X cybersecurity is something that we're going to address, and we're going to come with solutions in the future. But definitely, they are not the same solutions for the TCU, and the IVI is with even less intelligence. Even though it was used and proved to be a tool to attack a vehicle, it's my belief that if you just take it and separate it from the vehicle as much as possible and leave it with the minimum connection to the vehicle, it can be relatively well protected compared to the more, here we speak about simplicity and complexity. So the V2X and the TCU are complex devices, therefore they require complex security approach. However, the IVI is a bit simpler device and can be relatively be protected in a better fashion due to exactly those reasons. So different board games, different skill set, different rules, different. You cannot take an Ethernet, automotive Ethernet IDS, plug it into the IVI, into the TCU, and into the V2X, and think that they will provide a solution. You need to tailor each and one of them for their specific task.
Mm-hmm. Yeah, definitely. I completely agree with you there. All right, I think we have time for one more question here. You're always looking here, because this is a remote attack, right? You're always looking at the cellular communication channel. And until now, we've been focusing on LTE and 4G and stuff like this. Is there any type of additional security benefit that we will get from using 5G related technologies?
I think that mainly we'll get more pain in the cybersecurity. So 5G comes with a lot of value. Higher speeds, short round trip times. It's not another linear step in the cellular. It's disruptive. It changes quite a lot of things. The thing is that with 5G, we will go more to the connected gateway architecture, or a TGU, which is a combination between the gateway and the TCU, and it can be even a larger machine that will have the V2X embedded into it if 5G is going to be used. And there are two standards. One of them working on a similar to Wi-Fi, IEEE 802.11 variants, and the other one taking the cellular interface. It is my belief that eventually the V2X is going to use 5G as well. That means that you will have one interface in the vehicle. Today, if you have a TCU with the SIM card and you have an IVI with the SIM card and you have your insurance plug into the OBD with its own SIM card, and there are 5 people in the vehicle with their cellular phones, you have 7, 8 connections between the vehicle and the antenna, and the cellular network needs to chase each and every one of them along the road. When we move to 5G, the vehicle itself will serve as a picocell, as a small cell, a cellular cell on its own. So all the devices in the vehicle will be connected to one point that will serve as the interface to the cellular network. So this changes the topology, changes the paradigm of how a set of devices in a vehicle communicate with the cellular network.
Mhm.
That means that we keep in that device a lot of communication that needs to be inspected and needs to be separated, because you want to separate between the cellular phone and the TCU and the IVI, and everything goes through one place, but you need to keep them separated and secure. So a lot of values will be gained, but as anything in life, whenever you enjoy a cake, you also gain 1 pound of weight. So the same goes with this thing as well. You come with 5G, which will bring a lot of value to the industry. But the same with Ethernet and automotive Ethernet. You come with the new technology, a lot of value in it from one side, but along with it, new software, new bugs, new exposures, new risks. That's life.
So what you're saying is the security area is only going to get more fun, right?
This means job security for us.
Well, I love to hear that. All
Yeah.
right. Sorry, Gilad?
No, that's what I just said. It's job security for us, and we're waiting for this thing to come. We're ready.
All right. Well, um, Gilad, thank you so much for the nice presentation this evening. Really interesting stuff here. Love to see the different types of architectures and potential attack vectors. So thank you very much from my side and ASRG. Before we close, would you like to say anything in closing?
Just thank you everyone for joining this evening. I do plan, even though the schedule for next year is tight, I hope that I will have the opportunity to give a few more lectures. Specifically speaking about these TCU, you're welcome to visit our website. There is an article which describes everything that I showed today, and a bit more into detail, so you can reach this article. This article was published in Telematics Wire as well. So in the last issue of this magazine, you can also read the article. Be happy to be here again, and thank you, John, and thank you everyone for your for enabling me to be here this evening.
Gilad, as always, it's been a pleasure. Thank you very much. I think if anyone has further questions, you can find more information on the Arilou site there. You see it on the screen. If you feel like chatting with Gilad, there's his telephone number as well. So you just, dial through and talk to Gilad, the man. And All right. I think that's it for tonight. So, guys, everyone, thank you very much for joining. We will have another one not next week. The next webinar will be in January 2021. So, come back, see the new ASRG in 2021, and join us for many new webinar series that we have coming. All right, everyone, have a good evening, a good new year, and hopefully you get some vacation too the end of December.